Hey there, marketing researchers. In this video, I would like to show you how to take a conceptual conjoint study design and to actually implement that in SPSS. So let's start with an example I think I typically use in class at some point. Let's imagine that we are product designers for this product called the Noki. It's actually in the real world now, but I once found it on Kickstarter and I thought it was interesting. It's basically a Bluetooth-enabled lock. So I was imagining that I was the product designer for this product. Assuming all other features of this product were the same, there was 3 different attributes that I was imagining as being relevant to affecting how much someone was willing to pay for this product that I wanted to investigate a little more closely. So these 3 different attributes or variables were the locking mechanism strength, the battery life, and the backup key system. For the locking mechanism strength, I imagine there was 3 different levels. This product could just be made out of hardened steel, super hardened steel, or super hardened steel with an anti-picking technology. Now we would imagine that people probably prefer this version the most, but the real question is how much more would they be willing to pay if we spent the extra money to produce such a thing? So these are just different categorical bins, so we would probably say that this is nominal data, or if you really believe that it's clearly obvious that this level is the one that they'd pay the most for, and this one the least, you could say it's ordinal. For battery life, we're imagining 3 different scenarios. The battery could be 6 months, 1 year, or 1.5 years before it needs a recharge or replacement. Of course, we'd imagine people like this version the most, but the question is, will they pay enough for it to overcome whatever it's going to cost us to produce a lock that actually has that level of battery life built into it? So we call this is clearly ratio level data. And finally, is there a backup key system? Now in this case, there's not 3 different levels that we wanted to study. There's only 2. There's a manual key and no manual key. There's literally no other way to get into it other than the Bluetooth. So we'd be curious to see how people respond to this. Now, if we did a full factorial design, we'd have 3 by 3 by 2, 3 variable, 3 by 3, 3 by 2. So we'd have 18 different combinations. That's going to be a lot for any person taking our study. Fortunately, we can use SPSS to design a fractional factorial that'll reduce this combination of 18 down to a more manageable set for our experiment. So let's go ahead and proceed. Okay, so since we know what we would like our conjoint experiment to look like, since we have the attributes and the level specified, it's time to design our research plan so that we can, instead of having to do a full factorial, we can actually do a fractional factorial design. So in SPSS, we can just go to Data, Orthogonal Design, and we can generate this. And we have 3 different factors or attributes, and one's called lock, so that'll be lock strength. We have another one called battery, and another one is the backup system, whether there's a key or not. So for the lock, I can give it a label. The actual variable names, of course, need to be short, no spaces, no wildcards inside of them, but the labels can be anything. So I'll just say lock strength here. I can change that. Battery, backup key system. Backup for battery. It's battery life, clearly, there. And for backup key system. Okay, so we have our lock, we have our battery, we have our backup. Now we need to set the actual levels for each one of these variables. So for lock, we can go ahead and define the values. And in this case, we know that the lock strength, hard, super hard steel, and plus anti-picking technology is nominal data. We're going to treat it as nominal category, so we can just code them numerically sequentially, and we can give them a label that's useful to us. And this is what we'll always do whenever we have a nominal variable as one of the attributes. It's easiest just to give them sequential numerical codes. Okay, continue. Now for battery life, is different. We actually believe that it has a linear relationship to how much someone's going to buy, so it's a continuous variable. So when we define these values, the levels that we intend to study are 6 months, 12 months, and 18 months. So imagining that the unit that we're going to be studying is months, we'll put in 6, 12, and 18, 18 representing 1.5 years. So, and this is something, again, we'll always do whenever we have a linear or quadratic relationship that we expect to have between our attribute and our dependent variable in Conjoint, we will actually plug in the actual level of values that we think are relevant. Later, when it comes time to interpreting our output, we'll see why this is useful to us. Okay. And then finally, for our backup system, it's also a nominal variable, so we can just again use the 1 and 2 code. Okay, we've done that. All right, so we have a 3 by 3 by 2, so that's 18 potential combinations if we did a full factorial. So hopefully the fractional factorial system will reduce this, and it certainly will. And let's give this new data set a name. We'll call it Conjoint Plan Card Example. You can give it any name that's useful to you. And then we should set our random number seed to something. It doesn't really matter exactly what the numerical code is. It's just that since this is an iterative procedure, if you don't set a fixed seed number, when you go back and rerun this again later, it's entirely possible you might get a slightly different solution. So if we set the same seed number explicitly, every time we run this, we'll get the exact same outcome, and that's useful. Let's check our options. Minimum number of cases to generate. We don't have to worry about this. In this particular case, it'll solve. We have a very small factorial system here. And then for holdout cases, we don't want to create any holdout cases. In the world of conjoint analysis, sometimes we create these holdout cases that when we actually conduct the experiment, certain particular combinations are specified as test examples to verify the quality of the results. So in other words, if you're familiar with the idea of modeling on a test portion of a data set and then ultimately validating how well that model works based on a holdout sample, this is similar to that idea. So we've set this all up, and we can just hit paste now. So when we hit paste, a syntax file should open up, or if you already had a syntax file open, it would paste to the end of that. And sure enough, we see that it created the syntax for us here. So that's one straightforward way to generate an orthogonal design using just the manual input system. So we can run it, select and run the design. Sure enough, run the code, and we get this warning. The warning's a little strange because it says it warns you that it worked correctly. Okay, thank you. And we have our output here. And here's of the 18 potential combinations that we would have to study if we have done a full factorial. It turns out we only have to study nine combinations here, and it's this particular set of 9 combinations. And you can always toggle, if you had labels, you can toggle the labels on and off quite easily. Here to refer a little typo of what they are. So very good. So now we know exactly, when we study the 9, exactly what they should be. Piece of cake. All right, so let's take another look at this. This time we're going to use the actual syntax. We're not going to use the point and click interface, and we'll see how easy it is to generate the same exact output using a syntax-based approach. Okay, so this time we're going to pretend that we're going to just set this thing up again, only in this particular case, we're going to use the template syntax that I generated for you. In this case, so we have orthoplan here. We are requesting our factors. So what's the name of our attributes? Simple enough. We just replace the names of our attributes. I'll do the exact same thing I did last time. Battery. Backup. I can write in my descriptive labels, make sure I'm good about using the quote marks. Now remember, battery life, we need to change these values here because we know it's a linear relationship, so we should actually use the realistic numerical values that correspond to the levels. And we delete the third level here because we didn't have a third level, we only had 2. For holdout, 0, minimum, no minimums in this particular case. place, and then we give our out file a name. And again, we'll, in this particular case, I did in fact call it the conjoint plan card example, so we don't have to change this here. And remember, we don't have a working directory set. So when we save this, notice there's just a file name. So the question would be, where does the file go? And the question is, whatever is the default file that SPSS, folder that SPSS understands is where work is being done right now, is where that file is going to go. All right. Okay, and since we haven't had it, didn't specify that this will overwrite the file, we want to make sure we give it a different name than our previous example, which had the exact same version. So by doing this now, it'll write just fine. And we run the syntax and check under here. We should have a new data file open up. Boom. There we go. Now, since we use the same random seed, we should get the exact same pattern of 9 examples as we did from the earlier version. So let's verify that. Okay, so I pulled up both versions of the file after I ran them 2 different times. And I just want to illustrate to you, here is the plan that was designed using the point-and-click interface. On the bottom right here is the version with the syntax created. We had the same seed value set for both ones, a 2, 8, 6, 4, and they ultimately had the exact same code, 3 variables, the first one with 3 levels, the second one with 3 levels, and the third one with 2 levels. And sure enough, you'll notice that the pattern of combinations for the 9 cards that we need to generate for our experiment are exactly the same. Good stuff. Okay, so we've generated our orthogonal plan. Now that we know that this is the design we have to use, let's go ahead and create our experimental stimuli based on that. Okay, so I know how I need to create my experimental stimuli for my conjoint study. Let's take a look at the template I've built out to generate the stimuli. So here we go. I have an image introduction to the Noki. I have a little blurb that offers people some information about what the Noki is. We tell them that there's some new features that have to be finalized. We don't know how much they value the Noki depending on the different variations. We even tell them that they're going to see 9 different combinations, and we know the maximum price. Now in reality, for each person who takes a study, we're going to put these in random order, but we need to keep track of what the 9 combinations are, because it matters for us which combination they're seeing for each when we input the data later after we collect the results that the respondents gave us to the conjoint. So let's see, here's combination 1 of 9. Let's make sure it matches up with what we need to do. It's going to be super hard steel, 6 months of battery life, and the manual backup keys available. Very good. So this is great. So that means we could just create our next experimental stimuli. So now we're on version 2 here. Version 2 should just be hard steel, 12 months with manual backup. Okay, so just switch those. It's pretty good. You get the drift. At this point, I'm going to speed everything up and finish all these really quick. Just keep verifying that I'm doing it right. Okay. Okay, so I've completed all 9 combinations. If you're familiar with using mail merges in Word, it'd be pretty easy to have brought the data from SPSS into an Excel file, then reference all these and have these automatically populate in the correct sequence using a mail merge. But I judged it'd probably take me personally longer to set up all the whole mail merge correctly with the only 9 combinations. But choose whatever path works best for you. Now, when I've completed this, there's a couple of things I still need to do. I typed this by hand, so I'm going to go back and check and make sure I use the right word each time as I type this. I think I made some mistakes, so we'll look at that. I'll do that and handle that in the background. And secondly, I should keep in mind that I'm only showing you this part here where it says combination 1 of 9, 2 of 9, 3 of 9. This is for us. I wouldn't actually show this to the person who's taking my experiment, because remember, I'm going to take these 9 combinations and randomize their order. And when I do that, when the person's taking the experiment, I don't necessarily want them to know which number it is. It might contaminate how they respond to things. They might start generating theories about what each combination means. So this is really for us. I would end up deleting this. Okay. So I'm gonna do a little cleaning up of these, and then we'll proceed with showing how the rest of the study is done. Okay, so I went through and clarified and made sure I had all my attribute levels written the same way each time. I'm zooming out, showing you all different 9 combinations. So there's a bunch of different ways we could do this actual study. In this case, I might imagine the easiest way to do this would be I would print out the 9 versions, randomize their order, and hand them to somebody and just let them flip through and complete the numbers. This could easily enough be generated in Qualtrics using the block randomizer design, basically create a randomized experiment using exactly the same approach. Doesn't really matter for our purposes, but one way or another, we need to now distribute this experiment and actually gather the data. So what we'll imagine we've done so far is we've deployed this experiment to one person. So now that we have the data in hand, it's time to make sure that we have the data file in SPSS set up correctly so that we can analyze it. So let's do that next. Okay, so we've collected our responses. We have 9 different responses from a single individual. We have a blank SPSS data file. Let's go ahead and set up the minimum requirements that we're going to need to be able to input this data. So we can go to variable view, create some variables. I'm gonna call this one name. We'll use that as the person's name, but we'll use a numeric code. Sometimes the conjoint analysis algorithm misbehaves when we're using text. So we'll put in numerical codes. And then we need to place these 9 different versions of the experiment in some order using a short variable name with a numeric at the end. So in this case, I'll use score 1, score 2, score 3. You get the idea. Okay, so we have those all entered. These are all numerics. Great. We can go back to data view. Okay, now regardless of what position a particular experimental respondent took the study, we need to make sure that the values we place here from score 1 to score 9 correspond to the order that was told to us in the conjoint plan. So in this case, imagining someone took this experiment, combination 1 of 9, maybe they typed in that they'd be willing to spend $27 here. And apparently people write in Comic Sans. So they put 27 here to this version, and this version, which was the second version, they typed in 37. And then I'll just imagine other values to illustrate this. So even though maybe the person took this version last when we randomized it, we need to make sure that it shows up in the second position in our data set. And now I'm just making up values because I just want to illustrate the idea here. The fact that I'm making up values could be problematic later. Some of these responses might be a little nonsensical. For example, maybe some of these that I've placed in here at random means that the longer battery life versions are scored lower. That would seem to be a little strange. So we'll see what happens when we actually run this analysis. So we'll give this person an ID code. Randomly call this 3333. That's the person. And let's imagine we did the study a second time. for our actual data set. We have 2 people, and this would just proceed on as we gather more data. Let's go ahead and save this. And I actually have a folder on my desktop that I called Conjoint Example. I'm going to refer to this and go, and I'm going to call it Conjoint Data, one word. Okay, great. So we have our plan. We made that earlier. We executed that plan. We've gathered data based on that plan, and we've inputted that data into a second SPSS data file. So based on this, we should have enough to actually run our conjoint analysis. So in the next phase, let's go ahead and do that. Okay, so we're ready to actually analyze the conjoint data that we've collected. So the best way to do this is we need to create a folder somewhere on our computer that's easily accessible. So Windows users, in my case, I placed a folder called Conjoint Example on the desktop. And here's the exact path name. We need this exact path name. I made this folder. And then the next thing I had to do was make sure that there's 2 files inside of here. One, this is the exact same conjoint plan card from earlier. See that here? And here's the conjoint data that we collected. They should be in the same folder. Now let's prepare our syntax. So I have a syntax file. Now this syntax file is open. The first part here, this is the ortho plan. We only use this to design the plan of the design. We're really done with this. We don't need this anymore. Now we're ready to actually analyze. So let's proceed. First, what we should do to make this work as easy as possible is we should use a little piece of syntax called CD. It just means change the working directory. And what you should do, placed around in quotes with a period at the end, is you should tell SPSS exactly what working directory folder all of the data files it's going to need to run the conjoint is located in. So obviously yours is not going to be C users Andrew desktop conjoint example. If you're a Windows user, it works with C : here. If you're or whatever your main drive is and wherever you put the folder. If you're a Mac user, it's a little different. You don't refer to the drive letter, and it's a / instead of a \. So go ahead and figure out how to refer to a file directory with your particular piece of hardware. Okay, so here's the conjoint analysis syntax that we're going to be using. We're going to have to set this up a little carefully here. So first of all, what's the name of our conjoint plan file? So it's looking for a particular file name. Ours is not this. Looking at my folder, it was conjoint plan card example. So I'm going to just copy that name here and paste it right there, still referring to it as a save file. Now where did the data come from? Again, I have to change the data file name here. It's conjoint data, so I can just borrow that. Again, paste it right here, making sure there's still a .save at the end. Now my scores are not pref1 to pref9. You might remember that I chose to use score 1 to score 9, and I need to type that exactly the same way. And and my ID is called name. Let's remember that as well. And our subject, what's the ID identification, it's name in this case. And now our factors, what are the names? Let's see, is it lock, backup, and battery? Making sure I verify that it's exactly the same. It will not work otherwise. Check my plan card, that's where that lock, battery, and backup, all capitalized. So that should be okay. Okay, and then and this is the part where I have to tell SPSS what I thought the theoretical relationship between the attribute and the outcome variable, which is how much someone will pay, should be specified. So I did think it was discrete or nominal between lock and backup. I could also do it this way. Just put a model after each one. And then for the battery variable, I thought there was a linear relationship between the two, so I'll specify linear. Plot all, that's just going to give me insights into all the different output that comes from this. a utility file. This is useful. I'm going to call this utility output. It's going to make this file when we run it. So everything should be good here. Make sure we set the working directory as we run this. So we can select all this. It'll run this code, then run the rest. Let's go ahead and go. Okay, so we have able to generate our output. Let's take a look at our output here. So starting with the conjoint analysis output, warnings, no reversals occurred. Good, that's great. Reversals are when someone's weighting of a variable that we predicted to have a linear relationship sort of flips or in some unexpected way. For example, here, we wouldn't expect people to dislike 18 months battery life more than 6 months. But let's keep in mind that the data that I typed in this particular example was random, right? I just punched in some numbers. So people's particular values here in these particular results might seem a little silly, and that's just because it's not real people. So we have 3 levels, and 2 levels for our model, which is exactly what we specified. Here's our estimates for subject 1, how much importance they place on it, and so on. Here's subject 2. We really shouldn't worry about these too much because they're pretend. Here we can see that just plotted in chart form. And again, in this sort of silly example, we can see that lock strength seemed to be the most important issue for both people. And then the summary is where it just literally aggregates however many respondents together into sort of an overall aggregate model. Okay. And in this particular case, because we measured things in US dollars, the utility estimates that we're seeing here, these utility coefficients, can literally be interpreted in dollars as well. So whatever our dependent variables was modeled as is what we will have. Okay. All right, let's take one more look at the data file that should have been saved. So we go back to our folder. Remember, we told SPSS to work always within this folder, so it created that utility output for us. Great. You can open that up. And what we see here is this individual, and these are their model parameters. Let's see. Since we had 3 different locking levels and we interpreted it as discrete or nominal, there should be 3 parameters. For backup, there was only 2 different backup key levels, so there's 2 parameters. And for battery life, it was linear, so we only need a single coefficient to specify that linear relationship. So we should have known that we were only going to get 1 parameter here, even though we had 3 different levels of battery life. And then the scores here, these are for the 9 different versions that the people saw. According to our model, not what they actually put into the data set, we know these are different, but according to our computational model, these are the values we estimate the person literally values these products at in US dollars. And again, it's US dollars because they inputted their results in US dollars. So these scores aren't very useful to us because we know that there's actually 18 different combinations of the Noki, but we only see 9 scores here. So the scores are only calculated for the 9 combinations that were actually shown, but we can use the model here to estimate for any one of the 18 total possible combinations. So let me show you how that's done quickly. So in this case, I'm going to just copy, I'm hitting the Control C here, copying this data. I'm going to paste it right into Excel. Okay, so there's the values. The labels didn't come along with it, which is a little annoying. So we can go to variable view. You could grab these, copy them, go to Excel, and then paste them. Then we could copy it one more time, just go in here. We could do a paste special, and we can transpose it. There we go. So that's nice. Okay, so now we have the parameter estimates for each person. And let's set it up. Okay, so this is literally just sort of expressed as a typical model. For simplicity, let's just imagine we're only focusing on person 333 right now. Okay, so the constant's always going to be there. So let's imagine we're going to multiply it always by 1, so meaning it'll always be there. Now for the lock, there's 3 different lock types, and these are dummy codes because it's nominal. So exactly one of these 3 needs to be specified as a 1, and the other one's 0. For the backup, same thing. They're dummy codes, so one of them has to be activated, one type of backup, and the other one turned off. Then for battery life, it's continuous, and because we specify it's a continuous, variable, and linear, we know that we modeled between 6 to 18 months of battery, and even though we didn't actually study 14-month battery life, as long as we're within that min and max range, the model in theory should perform okay. So we can say prediction. So now we can start playing around with these values to make predictions for this individual. In dollars, you guys know what they're going to pay. So let's say dollars. So the model is pretty straightforward. We can do a sum product function here. Sum product. So we're saying for these values, take these values. What's going to happen by doing the sum product here is it's going to take each matching value in the array and multiply it by that value. So the constant we multiply by 1, so it'll just be the constant. Lock 1, multiply by 0, so it'll cancel out of the equation. Lock 2, since the 1, it'll actually reduce it by $7 because this person apparently, this particular version compared to the norm, values it $7 less. For this particular version of the backup, they're willing to pay an extra $2.58, so it'll multiply by that and bring it into the model. 0 cancel out. And for battery life, apparently in this person, again, remember this was made up data, so we get absurd results. For every additional month of battery life, they're willing to pay 86 cents less. Now that's really silly, but it is at least how this fake data was modeled, so we can hit return here. So according to this person, for this particular combination, we expect that they'd pay $27.68. So how do we try to find the version of the product that they want the most? Simply, well, we can just look at the coefficients. Apparently they like the third version of the lock the best. That was the super hardened steel version with anti-picking technology. So it multiplies by this now. Value goes up. They do in fact want the first backup version. And for battery life, again, this person's a little crazy. They apparently want the lowest battery life. So 6 is the only reasonable range. So there we go. So this should make it clear why it's really useful to perform a conjoint analysis and pull out the parameter estimates that come out of it. We can then start simulating and modeling different combinations of people's preferences or different attribute levels and see how it affects their preferences, in this case expressed as actual dollars. Good stuff.